Morning, Johnson. How are you? I believe you are doing very well. So, this happens to be our first class, and for the email I sent you earlier, that this topic is gravitational field. And before now, in your 10th grade or 8th or 9th grade, I believe you have learned something about gravitation, which is the effect of the gravity on a mass. So anything that has a mass comes under the effect of gravity. So we define gravitational field is a region or space around a mass which the gravitational force of that mass can be felt. So we're trying to say that when you bring a mass into a gravitational field, the mass will feel the effect of the gravitational field. Take for instance, you as a person is a good example of matter, right? You have mass, or we all have mass. Now when you make an attempt to jump, you discover that you are always coming down. You don't jump and keep going up, you jump and then return. The reason is because you are being influenced by the field called the gravitational field. So anything that has mass can be affected by the gravitational field. You understand? So the gravitation is the force of attraction exerted by a body on other bodies in the universe. So this gravity goes far and way beyond even the Earth. Gravitational force happens between planets, happens between any two bodies that have mass. So even in space, there is gravitational force between the sun and the Earth, between the moon and the Earth, between any two bodies that are in a system that basically relate together, right? You can see the planets, stars and galaxies all have this effect of gravitational field upon them. Now, in the course of trying to study gravity, a law was propounded by Newton, which is called the law of universal gravitation. The law of universal gravitation, what does it say? It states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and then inversely proportional to the square of the distance between them. A simpler way to put it is the force of attraction between two masses. As you can see, M1 is the first mass, M1, and M2. The force of attraction between these two masses is directly proportional to the product of their masses. What do we mean? When I multiply M1 times M2, the force of attraction is directly proportional. That is, the magnitude of the force is equal to when I multiply M1 times M2. And then this same force is also inversely proportional to the square of their distance. So let's assume M1 to M2 is 2 meters. When I square 2 meters, I will get 4. Right? So you are saying that the force is also equal to 1 over 4 of their distances. You get that? Now, for every physical law, we have a mathematical representation. That is the only way we can grasp or express how we feel about something. Good. Now, remember the law say the force of attraction between two bodies is directly proportional. Now look at this equation number 1. Look at force. This symbol means directly proportional to the product of their masses. So look at this, M1 and M2. So F is directly proportional to this. Then equation 2 represent the second aspect of the law that says the same force is directly proportional. This is the symbol of proportionality to the inverse square of their distances, right? It's directly proportional to the square of the separation of distance. So when we combine the first one, equation 1, we combine the second one, equation 2, to give us equation 3. So force is directly proportional to masses. You can see this, and then 1 over r square. When we multiply this, it gives us the whole of this. And then in our 10th grade mathematics, we learned that if we want to remove a sign of proportionality, what do? We introduce an equal sign and a constant. So in this case, our constant is called G, which is universal gravitation. I hope you get that. Now, we should note that M1 and M2, they are masses of the two particles. Then this R is their distance, and then G is the universal gravitational constant as given by Newton. Now this constant have a value as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. So in all the calculations or all the problems relating to gravitational force that we're going to encounter, we will have to use this constant G, right? And the constant will always be given to you. If it is not given to you, if you can recall, that will be fine. Or if you have a formula table, you can always make reference to it. All right. To further substantiate what we have said, look at this activity. Look at this. Now, this is a virtual lab that can describe what we're trying to say. Now, this is a force. Look at this force M1. Okay. And look at this force M2. Now, look at, we said that the force of attraction is directly proportional to the product of their what? Of their masses. And then it's inversely proportional to the what? The distance of separation. Now, assuming I put this meter rule here, and then the distance between these two forces or these two masses is based on my meter rule. Let me make it 6. Good. Let me increase this mass to 200. Oh, 200. All right, 200. Now, you can see now, the first mass is 200, the second mass is 400. The force of attraction between them is 1 times 1.39 times 10 to the power minus 7 Newton. Now observe what is going to happen. When I bring mass close, when I bring M1 closer, discover that the force increases, right? When I take it back, the force decreases. The same thing with M2. When I take it back, the force decreases. You're seeing it. When you bring it close, it increases. What are we trying to say? The distance of separation, when the distances are closer, the effect of the force is stronger. If the distances are apart, the effect of the force is stronger. Now look at this. What will happen if the mass is increased? So let's check. We are maintaining the same distance. Let's increase mass 1 by, let's say, 3. Let's increase mass 1 to maybe 300. Now look at it. The force of attraction is 2.76. So let's increase the first mass and see what happens. You see, as we increase the mass, the force of attraction also what? Increases. We are seeing that. Let's try the second one. What about reducing the mass? As we reduce the mass, we are seeing the force of attraction. So the masses also play an important role in the force. So if the bigger the masses, the bigger the force. Remember we said the force of attraction between these two masses are directly proportional to the product of their masses. So if the masses are massive or big, the force increases. If the masses are small, the force reduces. If the distances are too much, the force reduces. And if the distances are so close, the force also what? Increases. So very good. So that's how much you can do. So I'm going to give you this link. You can go and play around it and understand what is there, and you could do something about it. But before then, let me take this one example. It says calculate the force of attraction between two objects of mass 10 kg and 50 kg respectively, which are 10 centimeters apart. So this is the constant I was talking to you about. G as 6.67 times 10 to the power of minus. So how do we do that? Now I can use my virtual lab to solve it before we use calculative method. Now look at this. Let's try this. They said that one of the masses is 10, so let's reduce this to 10, and the other mass is 50, so let's make this 50. Good. Then the distance is 10. Distance between them is 10. Okay, distance between them is 10. Good. So I have a 10 meters distance, one mass is 10, so you can see the product or the force of attraction between them is 5.39 times 10 to the power minus 10. If we use a calculator to do this analysis, you discover that it gives us the same result. So I hope with the little explanation. If there's any question you would like to ask, I'll be taking them now before we use the formula method to do our evaluation.